Hi dear student, welcome to my channel Education Shop. In this video, solve problem 3.25 from the book Heat and Mass Transfer by A.Çengel 6th edition. This statement is relevant about heat transfer through a double pane window. In this figure you can see the double pane window. Let's come toward its statement. Consider a 1.2 meter high and 2 meter wide double pane window consisting of two 3 millimeter thick layers of glass. Thermal conductivity is 0.78 watt per meter Kelvin, separated by a 12 millimeter wide stagnant air space. This is a stagnant air space between these two glass, and its thermal conductivity of this stagnant air is 0.026 watt per meter dot Kelvin. Determine the steady rate of heat transfer through this double pane window and the temperatures of its inner surface for a day during which the room is maintained at 24 centigrade, while the temperatures of the outdoor is -5 centigrade. Take the convection heat transfer coefficient on the inner and the outer surface of the window to be H1, that is 10 watt per meter square dot Kelvin, and H2, that is equal to 25 watt per meter square dot Kelvin. Disregard any heat transfer by radiation. This is the inside, this is the outside of the window. This is the first layer. Its thickness is x1, and the stagnant air between these two glass and its thickness is x2. The thickness of the third layer is x3. If you see in the figure, the thickness of first layer and the third layer x1 and x3 is equal, so we can say that x1 is equal to x3 just by figure observation, and its value is equal to 3 millimeters. In other words, we can write as 3 multiplied 10 to the power minus 5 meter. And the thickness between these two glass is x2, and in between these two glass the stagnant air is provided, whose thermal conductivity is 0.026 watt per meter dot Kelvin. This is, let's say, the first layer, this is second layer, this is third layer. The thermal conductivity of the second layer is 0.026 watt per meter dot Kelvin, and its thickness is x2, that is 12 millimeter, or in other words 12 multiplied 10 to the power minus 3 meter. The thermal conductivity of the first layer and the third layer is the same because it is glass, that is same in nature, same in dimension, and it is 0.78 watt per meter dot Kelvin. The convection heat transfer coefficient inside the window is H1, and it is 10 watt per meter square dot Kelvin, and H2 outside the double pane window, that is H2, is 25 watt per meter square dot Kelvin. The inside temperatures of the room is T infinity 1, that is 24 centigrade, and the outside temperature is T infinity 2, that is -5 centigrade. The height of this window, this is the height of the window, is, let's say, H. This is the width of the window, that is W. H value is 1.2 meter and the width value is 2 meter. This is the given data that is provided in the statement. What is the required data that have been asked in the statement? To find the amount of heat transfer through this double pane window and the temperatures at this surface and the inner surface temperature of the glass is, let's say, T1. These two are our requirement, and in order to find this we have provided this. Now come toward its solution. First of all, the area of this double pane window is equal to H multiplied with, what is the H value, that is 1.2, and the width value is 2, that is equal to 2.4 meter square. Now next, let me draw the thermal resistance network diagram for it. Here the temperature is, we know that is T infinity 1, the temperature is T infinity. This is the higher temperature, this is the lower temperature, so the heat is transferred from higher towards lower. When the heat is transferred from higher temperature towards lower temperatures, some resistance is offered to it. First resistance that is offered to the heat transfer is the Ri resistance inside the window. Now the resistance offered by this, the first layer of the glass, that is R1. The second layer, in which the stagnant air is provided between the two glass, that is R2. Now the resistance that is offered to the heat transfer by the third layer, that is the second layer of the glass, that is R3, and the resistance to the heat transfer outside the window, that is R0. This is Ri, resistance inside the window. The temperature finally dropped to T infinity 2, and the temperature is T infinity 1 inside the window. We will first find each value of the resistance, and then we sum up and we will find the total thermal resistance for it. As we know that if I draw the temperature versus resistance to the heat transfer graph, the temperature drop gradually as it passes each resistance that is occur to the heat transfer, and finally the temperature drop to T infinity 2. Here the temperature value is -5 centigrade. Here the temperature value is 24 centigrade. The first resistance that is offered to the heat transfer is Ri, that is equal to 1 divided by HIAI, 1 divided by the HI value is, HI means H1, that is 10, multiply area 2.4. to solve, you will get the Ri value, that is equal to 0.0417 centigrade per watt. The resistance R1 by the first layer and the resistance offered to the heat transfer by the third layer, that is also glass, is the same, because this first layer and this third layer is glass and it is same in nature and in dimensions. That's why it will offer the same resistance to the heat transfer also. And we can say that R1 is equal to R3, that is equal to X divided by Ka. X is nothing, it is 3 millimeters. X1 is equal to X3, 3 multiply 10 to the power minus 2 divided by thermal conductivity. This K1 and K3 is 0.78 and area is 2.4. This simply solves and you will get that is 0.0016 centigrade per watt. The second resistance R2, the resistance offered by the stagnant air, that is equal to X2 divided by K2A. X2 is 12 millimeter into 12 multiply 10 to the power minus 3 divided by K2, that is 0.026 multiply area 2.4. Solve this on calculators and you will get the R2 value, that is 0.1923 centigrade per watt. Next is to find the R0 resistance. 1 divided by H0 A. H0 value is H2, that is 25. Just solve on calculators and you will get the R0 value 0.0167 centigrade per watt. The total resistance is equal to Ri plus R1 plus R2 plus R3 plus R0. Ri is, just simply write the corresponding value of resistance and you will get the total resistance by adding it on calculator. The total resistance, you will get its value, that is 0.2539 centigrade per watt. Now the amount of heat transfer through this double pane window is equal to change in temperature divided by the total resistance in between these two temperatures. Inside temperature is 24 centigrade minus outside temperature is -5 centigrade divided with total resistance 0.2539. Just simply do this on calculator and you will get the total heat transfer through this double pane window, that is 115 watt. This is our first requirement. The second requirement is to find the inner surface temperature of the glass. We know that Q dot is equal to T infinity 1 minus T1 divided by the resistance that is in between this T infinity 1 and T1 is only one resistance. Here you can see, here the temperature is, the inside temperature is T infinity and the surface temperature here is, let's say, T1, and there is only one temperature in between these two temperature, that is Ri. That's why we will only put the Ri value in order to find this T1 value. Ri, rearrange these equations for T1. Multiply both sides Ri, this will cancel out with this, shift this minus Ti to this side and this term to that side, and we can say that T1 is equal to T infinity 1 minus Ri Q dot. Now just simply put the value, and the inner side temperature is 24 centigrade minus Ri is the inside resistance to the heat transfer, that is 0.0417, and the amount of heat transfer to this double pane window 114. Simply do this on calculator and you will get the inner surface temperature of the glass, that is T1, and it is 19.2 centigrade. And this is our final answer that has been, and this is our final answer that is asked in the statement. Please subscribe my channel if you haven't subscribed yet. Thank you so much.